So the way the story is going to break down is we're going to have two walls that are both made of plaster and glass. The first wall has 40 square feet of glass and 60 square feet of plaster, or more plaster than glass. And it lost an amount of heat, 1,920 BTUs of heat. Now, BTU is British thermal units. It's a way of measuring energy. Other forms of energy you might hear would be, say, calories. You might also hear joules. But it's a way of measuring heat in this case. And what we're going to be looking at is a second wall. We're going to compare these two walls. So first wall, more plaster than glass. There's 100 square feet total, and it lost 1920 British thermal units of heat. Second wall. So the second wall, with 10 square feet of glass and 100 square feet of plaster, lost 1,160 BTUs of heat. Now, this wall is actually bigger, and so it's 110 square feet. And the bigger a wall is, the more surface is being exposed, say, to the cold. Let's say this is a wall in a house. So it would sort of stand to reason that the bigger the wall, the more heat it's going to lose. But this wall is different. The other wall lost 1,920 BTUs. Much more than this 1,160 BTUs. But this is a bigger wall. How come it's losing less heat? Should be losing more heat. Well, it has something to do with the materials. There's 10 square feet of glass, 100 square feet of plaster. Again, more plaster than glass. Think of the glass as being like a window. But there's a lot less glass than plaster in this wall than, say, in the other wall. The other wall, you had 40 square feet of glass versus 60 square feet of plaster. They're much closer to each other in terms of amount. So glass tends to lose heat more than plaster. Now, this you don't need to know to do the problem, but the results here sort of make sense. So an insulating plaster is going to keep you from losing heat. Glass oftentimes lets heat just leak right out. That's why it's very important, at least to me, I think it is, that if you're looking for a house, you have those double paned windows. So you have glass and glass, but there's some air in between. And ideally, a vacuum tends not to always let heat pass through as much, compared to like a solid object or a wall that heat can pass through very easily. So big fan of double pane windows. So we've got these two walls. Now what we're looking for is this. So what is the heat loss per square foot for the glass and plaster? So let's say we don't know anything about glass losing more heat than, say, plaster, or glass allowing heat to pass through more than plaster does. All we know is we have two different walls with different amounts of glass and plaster in each of them. Can we figure out how much heat loss is occurring per square foot of glass and per square foot of plaster? So again, we want to break this down into knowns and unknowns. So what do we know? Well, let's make this a little organized. The first wall. Well, it has 40 square feet of glass. Has 60 square feet of plaster. And this might be kind of interesting, but the total square feet is 100 square feet. And we may not need this or not, but it's interesting that maybe we might. We also know this. It lost 1,920 BTU. So this is what we know about the first wall. 40 square feet of glass, 60 square feet of plaster. The total size of the wall, 100 square feet. And it lost 1,920 BTUs. Second wall. 10 square feet glass. 100 square feet plaster. It's 110 square feet total. How much heat did it lose? Well, a lot less. 1,160 BTU. So this is what we know. We know the size of the walls. We know how much is glass, how much is plaster, and we know how much heat the walls lost. Now let's take a look at our unknowns. Well, for this question, the unknowns, it's pretty much the thing they're asking us for. What's the heat loss per square foot for glass and plaster? We have no idea about that. So heat loss per square foot glass, heat loss per square foot plaster, the things that they're asking us for. Now, there might be something else that we also don't know, and this requires a little outside science, sort of a math trick of sorts. but it's dealing with rates. So I'm going to put an little star here, or asterisk, rates. We might want to look up something about rates. And the rate we're looking for is this. Rate of loss per square foot. The rate of loss per square foot times square feet equals heat loss. Let me amend this here of heat loss, not just any loss, heat loss. The rate of heat loss per square foot times square feet gives total heat loss. So this is a little idea. Let me give you an example of how rates work. So if the heat loss is 100 BTUs per 1 square foot times 20 square feet, the heat loss will be 2,000 BTUs. So we want to bring in this idea of rates. And this becomes a very important idea. So if we're not familiar with rates, it doesn't hurt to look something up or maybe ask a question. Rates that you're very familiar with. Miles per hour. So in this one, when you multiply by the number of hours, you'll find out the total distance you've traveled. So for this one, it'll be rate times time equals total distance. So if we're going 50 miles per hour, 50 miles for 1 hour times, let's say we drove for 5 hours. Well, 50 times 5 will give us 250 miles. So that's the idea of rates. So what we're looking for is heat per square foot, heat per square foot. We're looking for rates. Any questions about that? So what we're going to do, let's let X, let me make sure I'm going to use the same setup in the text. So this will be heat loss per square foot of glass. Let that be X. And then Y is heat loss per square foot of plaster. So we're looking for two rates, the amount of heat lost per square foot. The first rate is when that square foot is made of glass. The second rate is when that square foot is made of plaster. So now we're going to try to come up with some expressions. So heat loss due to glass. Well, first off, again, the rate of heat loss, I'll restate this. The rate of heat loss per square foot, and I am going to state it sort of generically, it could be glass or plaster, times square feet. This will give us the total heat loss. So if we want to find the total heat loss for glass, we want to take the rate of heat loss for glass, which we don't know, and multiply it by the square feet of glass. So let's take a look at this. Now the rate for the heat loss for glass we said was X. So this will be X times the square feet of glass. And then for plaster, well, this will be the rate of heat loss for plaster per square foot, or Y, times the square feet of plaster. Now we have one more equation. So we've taken this, the rate of heat loss times square feet is the total heat loss for that substance. So the total heat loss for glass will be the rate of heat loss per square foot for glass times the square feet of glass. The total heat loss for plaster will be the rate of heat loss per square foot of plaster times square feet of plaster. There's one more sort of expression we want to look at. The total heat loss for the wall, for any wall, it'll be the total glass heat loss plus the total plaster heat loss. So this is digging a little more into the science behind the problem. So let's start talking about these two walls. Now we're going to try to form some equations. Now, let's talk about wall one. Well, the total heat loss Well, it's going to be X times the square feet of glass. So the total heat loss for glass in this first wall will be X times, and then how much glass is in this wall? Well, there's 40 square feet. So the total heat loss due to glass will come out to 40 X. And then finally, the total heat loss for plaster well, it's the rate of heat loss for plaster times how much plaster is in this wall. Well, the rate we said was Y. The amount of plaster, 60 square feet, or 60 Y. So now we have expressions for how much heat was lost from the glass in this wall and how much heat was lost from the plaster in this wall. Now we know something about this first wall and heat loss. So the total heat loss is 1,920 BTUs. Now, the total heat loss is the heat loss due to glass and heat loss due to plaster. So that means this is that equation we saw earlier before we started working with this wall 1 in this current step. We know the total heat loss for glass was 40X. Total heat loss for plaster, 60Y. And this is 1920. So that gives us our first equation. Now, questions about that? Now take a look at wall 2. So for wall number 2, well, the total heat loss due to glass is the rate of heat loss, X, times how much glass is in this wall. Well, that's just 10 square feet, or 10X. Now to plaster, well, it's going to be like with the second wall. It's the rate of heat loss, which is going to be Y, times how much plaster is in this wall, or 100 square feet, or 100 Y. So now we've got the total heat loss due to glass, we have it due to plaster, and we also know something else about this wall. The total heat loss for this wall is 1,100 60 BTUs. Now again, this total heat loss for the entire wall, well, the heat's being lost for two things, through the glass in the wall, through the plaster in the wall. Total heat loss glass plus the total heat loss plaster is going to be equal to the heat lost through this wall. So that means 10x plus 100y is 1160. And that gives us the second equation. And I'm using the same x and y as I did before. And excuse me, the reason I'm doing that is I'm assuming these two walls are built out of the same glass and the same plaster. They're not two different types of glass and not two different types of plaster. So now let's take a look at our system of equations. So we need to solve this system of equations. And I'm kind of keen on the elimination method or the addition method. And what I'm thinking is multiplying through this equation by -4. Multiply both sides by -4. -40x minus 400y. And what's that going to be? Let me see. -4,640. So this will become our new second equation. So I'm going to adjust my system here. So what I'm going to do, I'm going to add the left sides together and then add the right sides together. So if we add the left sides and add the right sides, we're going to get a new third equation, but hopefully one with only one variable, which we can then solve for that variable. And it's going to work out because 40 and -40, they're going to cancel out. So those will go. 60 -400, -340. Let's see, -4,640 and 1920. Let me do some work on this. Just use the calculator real quick. negative 2720. So now we've got an equation that just contains y. So we can solve this dividing both sides by negative 340. We'll get y. What happens when we divide that by negative 340? Y will be 8. So we found y, and remember, y is a rate. So that's the amount of BTUs lost per square foot. It's 8 BTUs per square foot, and y represented the rate of loss for plaster. Now we just need to figure out the rate of loss for glass. So I'm going to go back to this first equation. Well, this time we know y is equal to 8. That'll be 480. And now we solve for x. That'll give us 1440. Divide both sides by 40. Let's see here. We'll get 36. So x, or the rate of loss for glass, is 36. So y was 8, x is 36. Y was plaster, x is glass. And that actually makes sense. At least it corresponds with to an extent, the real world. Glass tends to lose more heat than plaster, so we'd expect the rate of heat loss for glass to be larger than the heat loss for plaster. So any questions about that? Any questions about rates, how to deal with rates? So that might be, if you're comfortable with rates, you can kind of blow right through that part real quickly. If you're not comfortable, it might take a little bit of research off to the side. All right, so one more problem from this section I want to do, and it has to do with interest rates. Let's see here. All right, pardon me. So I'm going to look at example 2. You have $50,000 to invest. And let's see here, 2 accounts. See, 7%. So you've got $50,000 to invest, and you can invest it in two accounts, 15% interest or 7% interest. Interest is sort of like rent on money. When you put money into an account or let someone borrow money, they have to pay you something for that because they're using that money and you aren't. It's kind of like renting somebody an apartment. They're using that apartment and you don't get to, so they're going to pay you something for that. We call that payment rent. And when you let someone borrow money or use your money, then they're going to do the same thing. They're using something that's yours because they're using it. You don't get to use it, so you're going to ask them to sort of pay for that privilege. And when it's money that they're using, borrowing money from you, they don't pay rent, they pay interest. But it's sort of the same idea. So one account's going to pay 15% interest. Another account's going to pay 7% interest. And you want to make sure that you earn at least $6,000 a year in interest. So how much should you put in each account? Now you might be thinking, well, this is sort of a silly question. Why not throw all the money into the 15% account? Well, first off, if these were like, say, savings accounts, I would agree. Just put it in the 15%. Why even mess with the 7? Today's savings accounts don't earn very much money. In fact, they earn hardly anything. I think it's usually like fractions of a percent. So, and that used to be a strategy people used for retirement. You would build up this huge savings account and you could live off the interest, was the claim. Well, that's dropped away now. So what people tend to do is they invest in the stock market. You get who puts together a collection of stocks, and they create sort of a portfolio. You invest in that portfolio. When you invest, is you're giving money to these companies that are in that portfolio, and they're going to use your money to try to make their businesses better. Now, of course, with stock is you get profit from that. They're going to ultimately give you some money back for that. So it's sort of like, in a sense, like rent. So what's going to happen here, and what's very common with the stock market, is most stock where you're going to see a huge increase in the amount of money you're going to get back, tends to be very volatile. In other words, it can go up and then it can fall down. So that's one kind of stock. And of course, there's a more stable stock where it sort of goes up a little bit. So you buy some of that stock, you're going to get a little bit back as it increases, or a little bit more in profit, not as much. So because high yield stocks with a high percentage yield can be very unstable, they can go up and then plummet really badly, maybe lose a whole lot of money for you. There's usually a balance in a stock portfolio. Low interest return stock tends to be stable. Ideally, it slowly goes up over time, but it's slow. You might have to wait a long time to make money off that. Maybe you'll wait too long. High yield, you're rolling the dice on this. You might get a real boom in the stock and it just shoots up in value and suddenly you're rich. Or it'll go up and then plummet and you could lose all your money. So what people tend to do is they tend to balance between the high yield and unpredictable stocks versus the lower yield but more reliable stocks. And so that's why you'd invest in two different portfolios or two different maybe companies. You wouldn't just throw all your money into this high interest return, because what they're not telling you here is usually the high interest return, there's also high risk of losing everything. Low interest return, more stable, least likely to lose a lot or anything, or let alone everything. So that's why there's sort of a choice here. That's why we're sort of wavering on this. So here's the way we calculate interest. But first, let me take a step back. Let's look at our knowns and unknowns. And I'm going to number the steps here. I didn't do it in the last problem. I'll number them here. So knowns. What do we know? Well, we have $50,000 total. We know that one account is 15% interest. It earns 15%. So one account earns 15 and another account earns 7. We also know we have a goal in this. We want to earn 6,000 a year. All right, so it looks like the call got dropped there. Not sure how much was missed on that. I'll take a look at the recording later and see. If I need to re-record something, I will. So again, this chart in general is just a good tool you can use for these types of problems. Have a column for the amount invested, column for the interest rate as a decimal, and a column for the interest. This row, 15% account. This row, 7% account. So I'm going to fill it out. Let's go account by account or row by row. So how much is invested in the 15% account? Well, it's just X. We don't really know. All right. So what's the interest rate as a decimal? Well, we convert this percent to a decimal. And the way you do that is you take your decimal point, you move it 2 spots to the left. And then the total interest earned. Well, that's the amount that's invested times the interest rate. Or 1,500 X. Now I go to the second account, the 7%. Again, we're not sure how much is invested yet. We just gave that a variable identity. So we'll call that Y. And then the interest rate as a decimal, well, again, take your decimal point, move it 2 spots to the left. And then to get the total interest earned, multiply the rate and the amount invested. And that's going to give you the interest earned. Now, in step 3, we want to build some equations here. And we're going to use this chart to do it. And again, I'm doing this a little bit different than the text as far as the numbering goes, because I have this extra step at the beginning where we break it into knowns and unknowns. But there's one thing that's going to stand out. However we choose to break up the money between these 2 accounts, the amount in the 15% and the amount invested in the 7%, they've got to add up to 50,000, because we're taking 50,000 and breaking it up into one of these 2 accounts. So we're going to get X plus Y is 50,000. So adding these 2 together will give us our first equation. Now, we also want to make sure that we earn $6,000 a year in interest. So that means the amount of interest for each account, if we add that together, we should get 6,000. That's our goal. So that means we're going to get that second equation. So now we got our system of equations. Now we can try to solve. So I'm going to do the substitution method for this. I'm going to take X plus Y equals 50,000. I'm going to subtract Y from both sides. So here's an expression for X. Now I'm going to take this expression for X and substitute it into the second equation. And the substitution, when we're using the substitution method, we've got to put it into the other equation. If we use this equation to get an expression for X, we have to substitute in the other equation. distribute the 1500s. So I'm going to combine like terms, in this case, combine the y terms. Solve for y. And so what we're going to get is $18,750. So this is how much they're putting in the 7% account. And I'm guessing the 7% account is maybe less stable than the 15%. You'll see what I'm getting at. Or this is sort of a risky gambler type investor. So let's find out how much goes in the 15% account. Now to do that, I'm saying we want to solve for x, but I say use the easier of the two equations. Now remember that earlier we had solved for x. We subtracted y from both sides, and we've gotten this expression for x. So now we can just substitute y into this. What does that give us? $31,250. So that's what we get in the two accounts. So I guess this is, maybe whatever reasons they invested in the larger percent account. Maybe they are relatively the same stability. So that's not always how it works in real life. It doesn't always. So any questions about this kind of problem? Again, use that box. For this type of problem, using that box will help set it up. And it'll give you the first column and the third column. You can build an equation from the first column and build a second equation from that third column. So that's 3.2. I'll get started in 4.1. The story problems take a little bit of time, and that's all right because they can be kind of tricky. If you have any questions on these over the weekend, definitely let me know. All right. So what I'm going to mention in 4.1 here, and just to get us started off, are some properties. And this is just to kind of set us up for what we're going to be doing. So solving linear inequalities. So we're going to take some ideas. This is very similar. In fact, it's almost exactly the same as solving linear equations. We're going to use the same techniques. The two big differences is when we multiply and divide by negatives, we got to be careful with that. And we'll go over it why. And then for number two, it's very common. In fact, most of the time when we solve these kinds of problems, we're going to get answers with infinite solutions. So the techniques we're going to use are exactly the same. We're just going to be careful of multiplying and dividing by negatives. And the answers we're going to get, instead of getting like x equals 4, we're going to get stuff like x is less than 4. In other words, all the numbers, the infinite amount of numbers that exist less than 4, that's going to be our answer. So we're kind of running out of time. I'll just go through these properties. I'll revamp through these again on Tuesday. I'm going to adjust the homework so only 3.2 will be due on Tuesday. So properties. These are going to be the same as if we're dealing with an equal sign. So if we have A less than B, well, if we add the same thing to both sides, we'll get A plus C is less than B plus C. So I'll give you an example. Three is less than 5. Let's add 2 to both sides. Or same thing. Adding the same thing to both sides doesn't change the inequality. It stays the same. So we can add the same thing to both sides. Same is true for subtraction. If A is less than B, then A minus C is less than B minus C. Or put another way, we're given 3 is less than 5, then 3 minus 2 will be less than 5 minus 2 or 1 is less than 3. So we can, as long as we add the same thing to both sides, we subtract the same thing from both sides, inequality doesn't change. What it was here, it'll be at the end. It's where we get to multiplication and division is where things change. And I think I'm just going to call it there for now. So real quick, I'll do a quick example. X plus 3 is less than 7. Again, we want to get x by itself, just like with linear equations. So we want to cancel the 3 on the same side with x. So as long as we subtract the same thing from both sides, the inequality stays the same. If x is less than 4. And oftentimes we're asked to graph this. Now, x is never equal to 4. So we're going to have a hole here, or a parenthesis. And we want all the x that's less than 4, but not including it. So the answer we're going to get is an interval of all the numbers less than 4. So questions about that? All right, well, that's it for today. I'm going to check that video and see if there's any sort of how bad that interruption was. And if I need to re-record something, I will. Other than that, have a wonderful afternoon. I'll try to get this posted as soon as possible. Again, the homeworks have been adjusted. I think they're a little more reasonable. And any questions that come up on the story problems, they can be kind of tricky. Let me know. Other than that, have a wonderful day.
Bye, have a good day.
Bye.